All right. My name is Joshua Kemble. This is live stream number 268. I am a art director. I've been doing that for about 8 years. I've been a freelance illustrator and graphic designer for about 20 years. And when I don't do illustration or graphic design or art direction at my full time job, I'm working on comic books, graphic novels like Jacob's Apartment, which is a slice of life coming of age story about Jacob and Sarah. It's a full color graphic novel that I wrote and illustrated, where it basically talks about Jacob, whose father is diagnosed with cancer, and how Jacob starts questioning his faith and his belief in God. And starts asking some really heavy existential questions. And meanwhile, Sarah is going through a breakup, and she starts kind of questioning her identity and her purpose in life. And both of them find each other drawn together in a doomed romance that's kind of equivalent to if you took Eternal Sunshine for the Spotless Mind, put it in a blender with Ghost World. That is Jacob's Apartment. And yeah, that's available at bookstores everywhere. There's also Two Stories, which is my graphic novel that I hand wrote, hand illustrated, and hand drew and hand lettered and a bunch of other handy stuff. And that is an autobiographical confessional graphic novel about trying to destigmatize hard conversations about mental health. So those are my two books that are available. Today, I'm going to be working on coloring. Let's see, page 75 of Not Death But Love, The Strange Supernatural Story of Elizabeth Barrett Browning. And I'll probably be working on that until about 2 a.m. and then I got to call it for the day. So I've been having streams on and off all day, and it's been a lot of fun. The last one we had Jim Lujan join us, and I encourage you guys to check out 267 as well as be subscribed to Jim Lujan's channel. He's hilarious. I think he's a genius, honestly, when it comes to animation and comedy. And I feel honored to have him as a friend and be able to kind of riff with him online about silly things like um, British gentlemen telling your mom jokes and other such things. So, anyhow, let's get to the art cam. I also am probably going to be watching. So, there's a guy I'm subscribed to on YouTube named Lex Friedman, who I think is pretty intelligent and interesting. He works at like MIT, and he had a conversation with Stephen Wolfram about Chat GPT and the nature of truth, reality, and computation. And I thought it might be really interesting, particularly in light of some of the stuff my friend Corey Kerr has been talking about. I think this might be relevant to that. Possibly talking about some of the potential pitfalls of AI. So we're going to be possibly commenting on that while we also work on coloring comics. So we're going to feed the brain on both the left and right side, right? Like we're going to do some fun art and utilize that left side, and then we're going to listen to some interesting conversation to kind of keep that right side of the brain stimulated. So that's basically my plan for the day. If you're tuning in, I hope you pick up a pencil or a pen or whatever you're working on and work along with me. I'm going to go ahead and put it on our art cam. Voila. And I need to put my brand up. My goodness, all out of sorts today. Okay, so we got our brand. So basically, this is the page that I toned when I was hanging out with Jim Lujan earlier today. And I'm going to be going through it. You're going to see multiple things, previous pages that I'll probably turn off the line layers on. So I have page 73 and page 74. And this, at least that way I can kind of pull from the colors I've already chosen for previous pages, which I think will be really helpful. Let's see here. Anything else before we get into commentary and stuff like that? I think that's about it till we get into commentary. So I'll go ahead and pull up our little commentary video. And we'll watch the video and comment on it. And in the meantime, I'm also going to wrap up my Memorial Day, which here's to my grandfather who served in World War II. I'm going to drink an 818 in honor of him, which is a IPA called a first stage West Coast IPA, which my coworkers were kind enough to get me a little 4-pack of these for my birthday. So I'm gonna go ahead and drink one of these in memory of my grandpa, who was in the Navy during World War II, and then we're gonna work on comics. Which what better thing to do at 12 midnight? And again, we're gonna go till about 2 in the morning. So if you're just tuning in, we have some pretty interesting stuff in store. We're going to listen to a conversation on Lex Friedman's channel with Stephen Wolfram and comment on it.
I can tell ChatGPT, create a piece of code and then just run it on my computer.
Yeah.
And I'm like,
that's actually pretty loud. Let me see if I can turn it down just a little bit, and we'll have to kind of see what happens here.
That sort of personalizes.
Okay, I think that'll work. I just got to turn it down even more.
For me, the what could possibly go wrong, so to speak.
Was that exciting or scary, that possibility?
It was
Oh, and one real quick thing. As we're kind of commenting on this video, I'm going to be making selections and color filling page 75. So that's what I'm going to be working on while we comment. Okay, let's continue.
A little bit scary, actually, because it's kind of like, if you do that, right, yeah, what is the sandboxing that you should have? And that's sort of a version of that question for the world. That is, as soon as you put the AIs in charge of things, how many constraints should there be on these systems before you put the AIs in charge of all the weapons and all these different kinds of systems?
Well, here's the fun part about sandboxes is the AI knows about them. It has the tools to crack them.
So here's an interesting thing. Lex Friedman also works, I believe, in AI. From what I understand, maybe I'm misinformed, but I think that's kind of his specialty. So this should be a really interesting conversation. Okay, so we're expanding our selection, and we're kind of gonna have to get in, probably fix these little tiny corners in our selection that didn't get selected by the magic wand. And let's continue this conversation. Let's listen to the rest of this conversation.
The following is a conversation with Stephen Wolfram, his fourth time on this podcast. He's a computer scientist, mathematician, theoretical physicist, and the founder of Wolfram Research, a company behind Mathematica, Wolfram Alpha, Wolfram Language, and the Wolfram Physics and Metamathematics projects. He has been a pioneer in exploring the computational nature of reality, and so he's the perfect person to explore with together the new, quickly evolving landscape of large language models as human civilization journeys towards building superintelligent AGI. This is the Lex Friedman Podcast. To support it, please check out our sponsors in the description. And now, dear friends, here's Stephen Wolfram.
So here's the thing. I have no idea if this, I have not watched this conversation before, so this is a live reaction as I hear it. I have no idea if they're going to be like pro AI, there's nothing to worry about, or, more kind of cautious about AI. I have no idea. It'll be interesting to kind of hear. Again, I like to listen to conversations that could be from people I agree with or disagree with. I just think it's very interesting to hear different people's fascinating takes on hot topics of the day. All right, let's continue.
You announced the integration of ChatGPT and Wolfram Alpha and Wolfram Language. So let's talk about that integration. What are the key differences from the high philosophical level, maybe the technical level, between the capabilities of, broadly speaking, the two kinds of systems, large language models and this gigantic computational system infrastructure that is Wolfram Alpha?
Yeah. So
so this is going to be interesting because I don't know a ton about coding or anything like that. And so it's going to be interesting to hear them get into like the specifics of, the different kind of systems that are out there. I think should be fascinating.
Does something like ChatGPT do? It's mostly focused on make language like the language that humans have made and put on the web and so on.
Yeah.
So, its primary sort of underlying technical thing is you've given a prompt. It's trying to continue that prompt in a way that's somehow typical of what it's seen based on 1 trillion words of text that humans have written on the web. And the way it's doing that is with something which is probably quite similar to the way we humans do the first stages of that, using a neural net and so on, and just saying, given this piece of text, let's ripple through the neural net one word and get one word at a time of output. And it's kind of a shallow computation on a large amount of kind of training data that is what we humans have put on the web. That's a different thing from sort of the computational stack that I've spent the last, 40 years or so building, which has to do with what can you compute many steps, potentially a very deep computation. It's not sort of taking the statistics of what we humans have produced and trying to continue things based on that statistics. Instead, it's trying to take kind of the formal structure that we've created in our civilization, whether it's from mathematics or whether it's from kind of systematic knowledge of all kinds, and use that to do arbitrarily deep computations to figure out things that aren't just let's match what's already been kind of.
Oh, interesting. Okay, so it sounds like the difference that he's talking about is one is sort of an existing framework that it's then mimicking, and then it sounds like what he is working on is more of a system that would establish a lot of the rules and knowledge that we already have, but from that allow for computations that we may have never done before. That's interesting. At least that's what I gather from it. We'll have to kind of see. Again, a lot of this conversation might just float right over my head because again, I'm no expert on coding or AI, but again, it should be a really interesting conversation. We're going ahead and making selections. And right now, I'm going to work on this first panel. And what I'm doing is deselecting everything that is. Hang on a second. I'm deselecting everything that would be white in the image. Let me see. Are her. Yes, okay. I did make her sleeves have a little white trim to them. So that's good to know. So this part would be a deselection as well. And we'll get back into the conversation. Okay.
Said on the web, but let's potentially be able to compute something new and different that's never been computed before. So as a practical matter, what we're, our goal is to have made as much as possible of the world computable, in the sense that if there's a question that in principle is answerable from some sort of expert knowledge that's been accumulated, we can compute the answer to that question, and we can do it in a sort of reliable way that's the best one can do given what the expertise.
That's a little scary. I know it's weird. And we'll, I guess maybe they'll get into it, but like thinking about it, right? If we're having a computer compute something we've never been able to like answer from our existing information, who checks the computer data? Like, I don't know if that makes sense, but it's like, with Midjourney and these other programs, it basically like deconstructs an image and kind of reconstructs it with components that exist before, and it's kind of mimicking a human artist in very questionable ways. A lot of people have brought up potentially huge copyright issues with the way that AI works. But what's interesting is ChatGPT then is also trying to like kind of formulate and mimic like a human being writing something, kind of it's basically like a counterfeit. But what he's talking about is like creating currency, not a counterfeit, and that's kind of a scary thing because the counterfeit's pretty easy to measure whether it's successful or not. But you know what I mean? Like, I don't know, maybe this is going above my head, but like to me, my concern would be, if you have something that's not a counterfeit, like a counterfeit, you can look at and go, oh, okay, that looks like a dollar bill, right? But the actual thing, an actual new currency, how would you ever know how to judge it? especially if it's something that hasn't existed before. I wonder if they're going to get into that.
That our civilization has accumulated. It's a much more sort of labor intensive on the side of kind of creating kind of the computational system to do that. Obviously, in the kind of the ChatGPT world, it's like take things which were produced for quite other purposes, namely all the things we've written out on the web and so on, and sort of forage from that things which are like what's been written on the web. So I think, as a practical point of view, I view sort of the ChatGPT thing as being wide and shallow, and what we're trying to do with sort of building out computation as being this sort of deep, also broad, but most importantly, kind of deep type of thing. I think another way to think about this is if you go back in human history, I don't know, 1,000 years or something.
This guy has an awesome
and you
accent.
say, what can the typical person? What's the typical person going to figure out? Well, the answer is there's certain kinds of things that we humans can quickly figure out. That's sort of what our at our neural architecture and the kinds of things we learn in our lives let us do. But then there's this whole layer of kind of formalization that got developed which is the kind of whole sort of story of intellectual history and whole kind of depth of learning. That formalization turned into things like logic, mathematics, science, and so on. And that's the kind of thing that allows one to kind of build these towers of sort of towers of things you work out. It's not just I can immediately figure this out. It's no, I can use this kind of formalism to go step by step and work out something which was not immediately obvious to me. And that's kind of the story of what we're trying to do computationally, is to be able to build those kind of tall towers of what implies what, and so on. As opposed to kind of yes, I can immediately figure it out. It's just like what I saw somewhere else in something that I heard or remembered or something.
So basically, it sounds like they're trying to make something generative rather than derivative. That's what I'm gathering from it, which is a little interesting. Again, that's such a weird thing because, again, how do you even measure a generative process if it's not a mimic? Like, ChatGPT is a mimic. So like if ChatGPT is doing like a poem or something, it's pretty easy to measure its effectiveness and its convincingness. But if it's writing something entirely new or coming up with a new structure or a new form of writing, how would you even know to judge it? It's interesting. This will be a really fascinating conversation.
Something like this.
What can you say about the kind of formal structure or the kind of formal foundation you can build such a formal structure on? About the kinds of things you would start on in order to build this kind of deep computable knowledge trees?
So the question is sort of how do you think about computation? And there's a couple of points here. One is what computation intrinsically is like, and the other is what aspects of computation we humans with our minds and with the kinds of things we've learnt can sort of relate to in that computational universe. So if we start on the kind of what can computation be like, it's something I've spent some big chunk of my life studying.
Interesting.
Imagine that we usually write programs where we kind of know what we want the program to do, and we carefully write many lines of code, and we hope that the program does what we intended it to do. But the thing I've been interested in is if you just look at the kind of natural science of programs. So you just say, I'm going to make this program. It's a really tiny program. Maybe I even pick the pieces of the program at random, but it's really tiny. And by really tiny, I mean, less than a line of code type thing. You say, what does this program do? And you run it. And big discovery that I made in the early 80s is that even extremely simple programs, when you run them, can do really complicated things. It really surprised me. It took me several years to kind of realize that was a thing, so to speak. But that realization that even very simple programs can do incredibly complicated things that we very much don't expect. That discovery, I realized that that's very much, I think, how nature works. That is, nature has simple rules, but yet does all sorts of complicated things that we might not expect. As a big thing of the last few years has been understanding that that's how the whole universe and physics works. But that's a quite separate topic. But so there's this whole world of programs and what they do. and very rich, sophisticated things that these programs can do. But when we look at many of these programs, we look at them and say, well, that's kind of, I don't really know what that's doing. It's not a very human kind of thing. So on the one hand, we have sort of what's possible in the computational universe. On the other hand, we have the kinds of things that we humans think about, the kinds of things that are developed in kind of our intellectual history. And that's, really the challenge to sort of making things computational is to connect what's computationally possible out in the computational universe with the things that we humans sort of typically think about with our minds. Now, that's a complicated kind of moving target because the things that we think about change over time. We've learned more stuff. We've invented mathematics. We've invented various kinds of ideas and structures and so on. So it's gradually expanding. We're kind of gradually colonizing more and more of this kind of intellectual space of possibilities. But the real thing, the real challenge is, how do you take what is computationally possible? How do you encapsulate the kinds of things that we think about in a way that kind of plugs into what's computationally possible? And actually the big sort of idea there is this idea of kind of symbolic programming, symbolic representations of things. And so the question is, when you look at sort of everything in the world and you kind of, you take some visual scene or something you're looking at, and then you say, well, how do I turn that into something that I can kind of stuff into my mind? There are lots of pixels in my visual scene, but the things that I remembered from that visual scene are, there's a chair in this place. It's a kind of a symbolic.
This is really interesting because there's been this whole discussion in art about the signifier versus the signified. And it usually has a lot to do with symbols and signs, meaning that quite often we're kind of reading meaning and reading into things by kind of using symbols. And symbols are kind of like one of the main forms of communication and construction of like language and identity and recognition and like visual language. And so it's interesting that this, like, one of the things that I find fascinating about AI, and again, it's a little scary to me. I'm not necessarily like a big fan of AI, but one of the things that I find really fascinating about it is the fact that like we have now a bunch of things that are coming up, like automated driving, other kinds of automation and AI that are starting to take things that were like ethical or theoretical considerations, and we're actually starting to have to like deal with them in reality. And so it's interesting hearing him talk about a symbol structure system of learning, because again, like that's something that's been discussed for years in the art world. It's just weird to see it, being applied in reality in science. That's a fascinating thing. Maybe I'm misreading that, but it seems pretty interesting.
Representation of the visual scene. There are two chairs and a table or something, rather than there are all these pixels arranged in all these detailed ways. And so the question then is, how do you take sort of all the things in the world and make some kind of representation that corresponds to the types of ways that we think about things? And human language is sort of one form of representation that we have. We talk about chairs, that's a word in human language, and so on. How do we take, but human language is not in and of itself something that plugs in very well to sort of computation. It's not something from which you can immediately compute consequences and so on. And so you have to kind of find a way to take sort of the stuff we understand from human language and make it more precise. And that's really this story of symbolic programming. And what that turns into is something which I didn't know at the time it was going to work as well as it has. But back in the 1979 or so, I was trying to build my first big computer system and trying to figure out, how should I represent computations at a high level? And I kind of invented this idea of using kind of symbolic expressions, structured as it's kind of like a function and a bunch of arguments. But that function doesn't necessarily evaluate to anything. It's just a thing that sits there representing a structure. And so building up that structure, and it's turned out that structure has been it's a good match for the way that we humans, it seems to be a good match for the way that we humans kind of conceptualize higher level things. And it's been for the last, I don't know, 45 years or something. It's served me remarkably well.
So building up that structure using this kind of symbolic representation. But what can you say about abstractions here? Because you could just start with your physics project. You could start at a hypergraph at a very, very low level and build up everything from there, but you don't. You take shortcuts.
Right.
You take the highest level of abstraction, convert that, the kind of abstraction that's convertible to something computable using symbolic representation. And then that's your new foundation for that little piece of knowledge.
Yes.
And somehow all of that is integrated.
Right. So the sort of a very important phenomenon that is kind of a thing that I've sort of realized is just
that's interesting. So instead of kind of starting and building from the ground up and giving every single simple thing, they're kind of, it sounds like moving from the kind of more complex to the simple. That's interesting. I'm kind of curious where this is going.
It's one of these things that sort of in the future of kind of everything is going to become more and more important, is this phenomenon of computational irreducibility. And the question is, if you know the rules for something, you have a program, you're going to run it, you might say, I know the rules. Great. I know everything about what's going to happen. Well, in principle, you do, because you can just run those rules out and just see what they do. You might run them a million steps, you see what happens, etc. The question is, can you like immediately jump ahead and say, I know what's going to happen after a million steps, and the answer is 13 or something?
Yes.
And the one of the very critical things to realize is, if you could reduce that computation, there is in a sense no point in doing the computation. The place where you really get value out of doing a computation is when you had to do the computation to find out the answer. But this phenomenon that you have to do the computation to find out the answer, this phenomenon of computational irreducibility, seems to be tremendously important for thinking about lots of kinds of things. So one of the things that happens is, okay, you've got a model of the universe at the low level in terms of atoms of space and hypergraphs and rewriting hypergraphs and so on. And it's happening, 10 to the 100 times every second, let's say. Well, you say, great, then we've nailed it. We know how the universe works. Well, the problem is the universe can figure out what it's going to do. It does those 10 to the 100, steps. But for us to work out what it's going to do, we have no way to reduce that computation. The only way to do the computation, to see the result of the computation, is to do it. And if we're operating within the universe, we're kind of, there's no opportunity to do that, because the universe is doing it as fast as the universe can do it. And that's what's happening. So what we're trying to do, and a lot of the story of science and a lot of other kinds of things, is finding pockets of reducibility. That is, you could have a situation where everything in the world is full of computational irreducibility. We never know what's going to happen next. The only way we can figure out what's going to happen next is just let the system run and see what happens. So in a sense, the story of most kinds of science, inventions, a lot of kinds of things, is the story of finding these places where we can locally jump ahead. And one of the features of computational irreducibility is there are always pockets of reducibility. There are always places, there are always an infinite number of places where you can jump ahead. There's no way where you can jump completely ahead, but there are little patches, little places where you can jump ahead a bit. And I think, we can talk about physics project and so on, but I think the thing we realize is we kind of exist in a slice of all the possible computational irreducibility in the universe. We exist in a slice where there's a reasonable amount of predictability. And in a sense, as we try and construct these kind of higher levels of abstraction, symbolic representations and so on, what we're doing is we're finding these lumps of reducibility that we can kind of attach ourselves to, and about which we can kind of have fairly simple narrative things to say. Because in principle, I say, what's going to happen in the next few seconds? There are these molecules moving around in the air in this room, and oh gosh, it's an incredibly complicated story. And that's a whole computationally irreducible thing, most of which I don't care about. And most of it is, well, the air's still going to be here and nothing much is going to be different about it. And that's a kind of reducible fact about what is ultimately at an underlying level a computationally irreducible process.
And life would not be possible if we didn't have a large number of such reducible pockets.
Yes.
Pockets amenable to reduction into something symbolic.
Yes, I think so. I mean, life in the way that we experience it, that, I mean, one might, depending on what we mean by life, so to speak, the experience that we have of sort of consistent things happening in the world, the idea of space, for example, where there's, we can just say, you're here, you move there. It's kind of the same thing. It's still you in that different place, even though you're made of different atoms of space and so on. This idea that it's that there's sort of this level of predictability of what's going on. That's us finding a slice of reducibility in what is underneath this computationally irreducible kind of system.
That's interesting. So it's basically seems like it's talking about sort of the idea of like, weirdly enough, this might tie in a little bit with some of the other conversations we've been listening to, where you can kind of compute space, but at the same time, you don't have the time to process all the complexity of what is happening when you're like moving your body to a different space in a room. You just kind of accept the larger kind of reducibility of it, the action of like movement in a space, rather than having to kind of bog yourself down in the absurd complexity of everything that's going on around you with molecules and air and gravitational forces. And yeah, that's interesting.
And I think that's sort of the thing which is actually my favorite discovery of the last few years, is the realization that it is sort of the interaction between this sort of underlying computational irreducibility and our nature as kind of observers who sort of have to key into computational reducibility. Mm-hmm. That fact leads to the main laws of physics that we discovered in the 20th century. So we talk about this in more detail, but this is to me, it's kind of our nature as observers, the fact that we are computationally bounded observers. We don't get to follow all those little pieces of computational irreducibility to stuff what is out there in the world into our minds, requires that we are looking at things that are reducible. We are compressing, we're extracting just some essence, some kind of symbolic essence of what's the detail of what's going on in the world. That, together with one other condition that at first seems sort of trivial, but isn't, which is that we believe we are persistent in time. That is,
yes. So some sense of causality.
Here's the thing. At every moment, according to our theory, we're made of different atoms of space. At every moment, sort of the microscopic detail of what the universe is made of is being rewritten. Mm-hmm. And in fact, the very fact that there's coherence between different parts of space is a consequence of the fact that there are all these little processes going on that kind of knit together the structure of space. It's kind of like if you wanted to have a fluid with a bunch of molecules in it, if those molecules weren't interacting, you wouldn't have this fluid that would pour and do all these kinds of things. It would just be sort of a free-floating collection of molecules. Mm-hmm. So similarly it is with space, but the fact that space is kind of knitted together is a consequence of all this activity in space. And the fact that kind of what we consist of, sort of this series of we're continually being rewritten. And the question is, why is it the case that we think of ourselves as being the same us through time? That's kind of
that is so fascinating. I'm sorry, that's just really fascinating, because technically, like, the body you have a millisecond from now is different than the body you had before. Each cell in your body is continually changing. The different processes going on are continually changing. Since we're in this, and like, honestly, the air around you is continually changing. It's an interesting question of like, why do we view this as consistent? Like, that's fascinating. Interesting.
Key assumption, I think it's a key aspect of what we see as sort of our consciousness, so to speak, is that we have this kind of consistent thread of experience.
Well, isn't that just another limitation of our mind, that we want to reduce reality into some, that kind of temporal consistency is just a nice narrative to tell ourselves.
Well, the fact is, I think it's critical to the way we humans typically operate, is that we have this single thread of experience. You know, if you imagine sort of a mind where you have, you know, maybe that's what's happening in various kinds of minds that aren't working the same way other minds work, is that you're splitting into multiple threads of experience. It's also something where, you know, when you look at, I don't know, quantum mechanics, for example, in the insides of quantum mechanics, it's splitting into many threads of experience. But in order for us humans to interact with it, you kind of have to knit all those different threads together so that we say, oh yeah, a definite thing happened, and now the next definite thing happens, and so on. And I think, you know, sort of inside, it's sort of interesting to try and imagine what's it like to have kind of these fundamentally multiple threads of experience going on. I mean, right now, different human minds have different threads of experience. We just have a bunch of minds that are interacting with each other, but we don't have you know, within each mind, there's a single thread. And that is indeed a simplification. I think it's a thing, you know, the general computational system does not have that simplification. And it's one of the things, you know, people often seem to think that, you know, consciousness is the highest level of kind of things that can happen in the universe, so to speak. But I think that's not true. I think it's actually a specialization in which, among other things, you have this idea of a single thread of experience, which is not a general feature of anything that could kind of computationally happen in the universe.
Sorry, that is so interesting. And if you think about it too, it kind of makes sense because, like, can you imagine a mind where you have, you know, let's say your mind today had to process, you know, like 5 people's experiences, and how like identity shifting that would be. It would be hard to kind of, at least the way I think we're built, it would be pretty hard to even do anything because you just have so many different split kind of natures going on, or split ideas, split experiences. That's got to be, I don't know, that's interesting. The idea of like a single thread being like a really huge part of consciousness is a pretty smart observation, because we do all have like our own kind of sense of identity and experience, and that kind of helps us identify like what is and is not. Interesting. Okay, I think I'm following so far. It's pretty heavy, but following so far.
So it's a feature of a computationally limited system that's only able to observe reducible pockets. So
Yeah.
So I mean, this word observer, it means something in quantum mechanics. It means something in a lot of places. It means something to us humans,
Right.
as conscious beings. So what's the importance of the observer? What is the observer, and what's the importance of the observer in the computational universe?
So this question of what is an observer, what's the general idea of an observer, is actually one of my next projects, which got somewhat derailed by the current sort of AI mania. But
is there a connection there, or is that do you think the observer is primarily a physics phenomena?
Is it related to the whole AI thing?
Yes.
Yes, it is related. So one question is, what is a general observer? So, you know, we have an idea what is a general computational system. We think about Turing machines, we think about other models of computation. There's a question, what is a general model of an observer? And there's kind of observers like us, which is kind of the observers we're interested in. You know, we could imagine an alien observer that deals with computational irreducibility, and it has a mind that's utterly different from ours and completely incoherent with what we're like. But the fact is that you know, if we are talking about observers like us, that one of the key things is this idea of kind of taking all the detail of the world and being able to stuff it into a mind, being able to take all the detail and kind of, you know, extract out of it a smaller set of kind of degrees of freedom, a smaller number of elements that will sort of fit in our minds.
Nice. Kind of like looking at a bunch of trees and being able to work out a forest. I've been interested in trying to
characterize what is the general observer. And the general observer is, I think, in part, there are many, let me give an example of you know, you have a gas, it's got a bunch of molecules bouncing around, and the thing you're measuring about the gas is its pressure. And the only thing you as an observer care about is pressure. And that means you have a piston on the side of this box, and the piston is being pushed by the gas. And there are many, many different ways that molecules can hit that piston. But all that matters is the kind of aggregate of all those molecular impacts, because that's what determines pressure. So there's a huge number of different configurations of the gas, which are all equivalent. So I think one key aspect of observers is this equivalencing of many different configurations of a system, saying all I care about is this aggregate feature. All I care about is this overall thing. And that's sort of one aspect. And we see that in lots of different...
That's interesting. So like the ability to kind of target only simple, like basically look at a really complicated activity and isolate something that the things that are of interest to whatever kind of query you have. So it'd be almost like I'm trying to kind of work this out in my head. Again, I'm no MIT guy, but it sounds like almost like equivalent to if you look at a sunset, right? It can be pretty overwhelming. But if you just isolate the sunset into like, what colors am I seeing in the sky? And then like, what colors am I seeing? You know, if I even single it out more and go like, what colors am I seeing in the light? What colors am I seeing in the darkness? You know, then you can kind of measure it and you're getting a bunch of data, but you're pretty much disregarding any data that's not fundamental to the question that you're asking. And yet you're taking all the inputs of the question that you are asking. Interesting. Okay. That's what I get from it. Again, if I'm not processing it, if somebody's watching and they're an MIT scientist or a physicist, then feel free to critique.
Again, it's the same story over and over again, that there's a lot of detail in the world, but what we are extracting from it is something, a sort of a thin summary of that detail.
Is that thin summary nevertheless true? Can it be a crappy approximation?
Sure.
That on average is correct. I mean, if we look at the observer that's the human mind, it seems like there's a lot of very as represented by natural language, for example, there's a lot of really crappy approximation.
Sure.
And that could be maybe a feature of it.
Well,
but there's ambiguity.
Right. You don't know. You know, it could be the case. You're just measuring the aggregate impacts of these molecules, but there is some tiny, tiny probability that the molecules will arrange themselves in some really funky way, and that just measuring that average isn't going to be the main point.
Yeah.
By the way, an awful lot of science is very confused about this, because you look at papers and people are really keen. They draw this curve and they have these these bars on the curve and things.
Yeah.
It's just this curve, and it's this one thing. And it's supposed to represent some system that has all kinds of details in it. And this is a way that lots of science has gotten wrong, because people say, I remember years ago I was studying snowflake growth. You have the snowflake and it's growing, it has all these arms, it's doing complicated things. But there was a literature on this stuff, and it talked about, what's the rate of snowflake growth? And, it got pretty good answers for the rate of the growth of the snowflake. And they looked at it more carefully, and they had these nice curves of, snowflake growth rates and so on. Looked at it more carefully, and I realized, according to their models, the snowflake will be spherical. And so they got the growth rate right, but the detail was just utterly wrong. And
that's really interesting. So while they were focused on the growth rate, great, but then like they got the actual, the key thing they were supposed to be measuring wrong. So while they got a detail correct, they got the whole completely incorrect. Interesting.
And not only the detail, the whole thing was not capturing. It was capturing this aspect of the system that was in a sense missing the main point of what was going on. And
what is the geometric shape of a snowflake?
Snowflakes start in the phase of water that's relevant to the formation of snowflakes. It's a phase of ice which starts with a hexagonal arrangement of water molecules. And so it starts off growing as a hexagonal plate. And then what happens is...
You know what? I gotta say, before we continue, if there's anyone I know online who would know the actual shape of snowflakes and how they arrange themselves, it would be Adam Lohr. That guy is interested in shapes and the names of shapes.
It's a plate. Versus sphere versus.
Well, no, but it's much more than that. I mean, snowflakes are fluffy. Typical snowflakes have little dendritic arms.
Okay. Yeah.
And what actually happens is it's kind of cool, because you can make these very simple discrete models with cellular automata and things that figure this out. You start off with this hexagonal thing, and then the places it starts to grow little arms, and every time a little piece of ice adds itself to the snowflake, the fact that that ice condensed from the water vapor heats the snowflake up locally, and so it makes it less likely for another piece of ice to accumulate right nearby. So this leads to a kind of growth inhibition. So you grow an arm, and it is a separated arm because right around the arm it got a little bit hot and it didn't add more ice there. So what happens is it grows, you have a hexagon, it grows out arms, the arms grow arms, and then the arms grow arms grow arms, and eventually, actually it's kind of cool because it actually fills in another hexagon, a bigger hexagon. And when I first looked at this, I had a very simple model for this. I realized, when it fills in that hexagon, it actually leaves some holes behind.
How cool is that? That like to me, okay, snowflakes are fascinating, but I think it's amazing that just naturally these things form like totally symmetrical structures. It's kind of interesting to me, the symmetry in nature. That's a whole other thing, and that might be a fun wormhole to go down later on, is like just kind of listening to talks about symmetrical occurrences in nature. There's kind of like a natural repetition and symmetry to things that's really bizarre. It's kind of strange that that's the universe we exist in. But yeah, it's interesting. Okay, ladies and gentlemen, we have finished one panel. Excuse me. And I'm going to go ahead and save. I'm going to go ahead and color the stuff that I haven't colored yet as magenta. And let's see where we're at for time. It might be about time for a trailer. And look at that. It is about time for the first trailer. So if you're watching this and you haven't hit like, I would request that you hit like. And we're going to go ahead and watch a trailer. Let's do the Christmas trailer for Two Stories. I'll be right back. All right, we got Thomas Adams chiming in on the shape of snowflakes. He said, I thought it was the angle of the two hydrogen atoms on the water molecule. The two positive hydrogen atoms push away from each other, causing an angle that leads to a hexagonal shape. Interesting. Dude. I feel like the guy at the Pink Floyd light show, back in the 80s, the laser light show at the Griffith Park Observatory, where I'm just like, I kind of in theory understand lasers, but this is pretty rad. That's all I have to say. Thomas said, I know this angle lets water form a train that lets trees pull water up to heights that otherwise would not be enough pressure. Isn't that cool? I don't know. To me, it's cool we live in a world like that. Okay, let's continue.
So I thought, well, is that really right? So I look at these pictures of snowflakes, and sure enough, they have these little holes in them that are kind of scars of the way that these arms grow out.
Mm-hmm. So you can't backfill holes. So
they don't backfill. Yeah, they don't backfill.
And presumably there's a limitation on how big, like you can't arbitrarily grow.
I'm not sure. I mean, the thing falls through I think it does, it hits the ground at some point. I think you can grow. I think you can grow in the lab. I think you can grow pretty big ones. I think you can grow many iterations of this kind of.
Wouldn't that be cool? Like somebody grows like a gigantic snowflake. Now if I had time and I had access to the internet and was not bound to working endlessly day after day on this comic book, I would just Google the biggest snowflake in the world. Now I want to go on a snowflake rabbit hole. And ladies and gentlemen, this is how my brain works. Okay, let's continue.
Goes from hexagon, it grows out arms, it turns back, it fills back into a hexagon, it grows more arms again.
In 3D?
No, it's flat usually.
Why is it flat? Why doesn't it span out? Okay, wait a minute. You said it's fluffy, and fluffy is a 3-dimensional property, no? Or
no, it's fluffy. Snow is okay. So what makes we're really in a detail here, but
it's multiple snowflakes become fluffy. A single snowflake is not fluffy.
No, a single snowflake is fluffy. And what happens is, if you have snow that is just pure hexagons.
Here's what I love is like scientists debating what is fluffy. It's amazing to me. It's amazing. To me, it's amazing how much we know and how much we don't know. And how much we communicate and how much we miscommunicate. Like in this case, it seems like just the word fluffy itself is now in debate, where it's like, well, what do you mean by fluffy? Excuse me, sir, you said fluffy, and I dare say I don't believe that's what fluffy means. I think fluffy is a 3D thing. It's interesting. But it's amazing and fascinating. I love this stuff. I hope you're getting a kick out of it too. And by the way, Thomas, I hope you're having a good night. I'm going to be working for probably another hour and 10 minutes, and I appreciate the company whilst working on some comic books.
They can, they fit together pretty well. It doesn't have a lot of air in it. And they can also slide against each other pretty easily. And so the snow can be pretty, I think avalanches happen sometimes when the things tend to be these, hexagonal plates, and it kind of slides. But then when the thing has all these arms that have grown out, they don't fit together very well. And that's why the snow has lots of air in it. And if you look at one of these snowflakes, if you catch one, you'll see it has these little arms. And people often say,
dude, that's so interesting about how snow doesn't pack tightly. And the fact that might have to do with just the fact that it has tiny little arms. Now I want to see an illustration with a snowflake with a bunch of little arms that have hands. Christopher Runtman, if you're watching this after the fact, there's a 1-page comic cue for you. Snowflake with hands, like a hand-ridden snowflake.
No two snowflakes are alike. That's mostly because as a snowflake grows, they do grow pretty consistently with these different arms and so on, but you capture them at different times as they fell through the air in a different way. You'll catch this one at this stage, and as it goes through different stages, they look really different. And so that's why, it kind of looks like no two snowflakes are alike, because you caught them at different times.
So the rules under which they grow are the same. It's just the timing is.
Yes.
Okay, so the point is science is not able to describe the full complexity of snowflake growth.
Well, science, if you do.
Dude, Thomas dropping the science knowledge said that's why igloos keep you warm. Air is an insulator. And so there's packed air condensed within the snowflakes. And so like you're kind of creating like natural insulation. That's really fascinating. Wow.
Do what people might often do, which is say, okay, let's make it scientific. Let's turn it into one number. And that one number is kind of the growth rate of the arms or some such other thing. That fails to capture sort of the detail of what's going on inside the system. And that.
Ooh, I really like this point, because I've seen people do this with a lot of logic. Sometimes you can get so in the weeds with an issue or a topic, and it's interesting to me that comes to bear with with science as well. But it's like, I mean, you experience this issue a lot where like often if I talk to somebody who has a really simplistic understanding of how government works, and don't get me wrong, like, you can have different opinions on it and stuff like that, but sometimes I'll talk to somebody who has a theory of government that when you start talking to them about it, they don't quite understand like why governments arose, what function they have in society, like the history of it, like the more kind of epic view of it. And what you end up finding out is they've gotten kind of lost in the weeds, like, so they get stuck on like one little data point, and from that data point they just miss the entirety of the whole picture. So it's kind of like if I took this image that I'm working on right now and just isolated like one pixel, it'd be hard to understand the function of that pixel if you start focusing on it too much. And at some point, if you're focusing on just the pixel, you're going to lose the entirety of like the whole purpose of the pixel. So you might be like, what's the purpose of this pixel? That's insane. But it's partially because a lot of people can get, I think it's a pretty common thing. People call it like losing the plot, right? Where it's like you kind of get so stuck on like a story point that you lose the entire plot of the story. Yeah, that's interesting.
That's in a sense a big challenge for science, is how do you extract from the natural world, for example, those aspects of it that you are interested in talking about. Now, you might just say, I don't really care about the fluffiness of the snowflakes. All I care about is the growth rate of the arms, in which case, you can have a good model without knowing anything about the fluffiness. But the fact is, as a practical, if you say, what is the most obvious feature of a snowflake? Oh, that it has this complicated shape. Well, then you've got a different story about what you model. I mean, this is one of the features of sort of modeling in science, that, what is a model? A model is some way of reducing the actuality of the world to something where you can readily sort of give a narrative for what's happening, where you can basically make some kind of abstraction of what's happening and answer questions that you care about answering. If you wanted to answer all possible questions about the system, you'd have to have the whole system.
You know what's crazy? And I got to give you this this little tidbit of how this could apply to art. Back planning, right? And kind of like Corey Cruz talked about this, like kind of looking at a style and kind of figuring out like, what are the elements of this style that I could incorporate into my own work. A lot of it is this kind of process where it's like if you look at a good example, if you look at the Sistine Chapel, many people have described their experience of like visiting the Sistine Chapel, and it's just kind of overwhelming and stunning and kind of brilliant. And if you just focus on the whole, you can lose like all the little details that made the whole thing possible. You can lose like what medium was used, what studies were used, were there preparatory drawings, like how was this mapped out, how was it planned out, how was it executed, in what timeline was it executed, like little details. So I kind of get what he's saying about science kind of working on a reducibility model. This is an interesting thing that does tie into Francis Collins too. One of the things I liked about Francis Collins, he found it interesting as a scientist where everything's reducible and you're kind of trying to reduce things to the most simple element so that you can study it. And he thought it was really significant. And I kind of agree with this, that like, when they worked on, DNA, which is like one of the smallest areas you can get. The second you go that small, suddenly you have signifiers like, let's see here. So you have a language, and that's like semiotics are like really complicated. So it's like you've reduced and reduced and reduced and reduced, and then you get something semiotic, which is like that just is counter to the idea of everything in observation being reducible. That's it's just an interesting kind of thing. Okay, let's continue.
Because you might care about this particular molecule, where did it go? And your model, which is some big abstraction of that, has nothing to say about that. So, one of the things that's often confusing in science is people will have, I've got a model, somebody says. Somebody else will say, I don't believe in your model because it doesn't capture the feature of the system that I care about. There's always this controversy about, is it a correct model? Well, no model except for the actual system itself is a correct model in the sense that it captures everything.
That's a fair
question
point.
is, does it capture what you care about capturing? Sometimes that's ultimately defined by what you're going to build technology out of, things like this. The one counterexample to this is, if you think you're modeling the whole universe all the way down, then there is a notion of a correct model. But even that is more complicated because it depends on kind of how observers sample things and so on. That's a separate story. But at least at the first level, to say, this thing about, it's an approximation, you're capturing one aspect, you're not capturing other aspects. When you really think you have a complete model for the whole universe, you better be capturing ultimately everything, even though to actually run that model is impossible because of computational irreducibility.
That's a really good point. Let's see here. Thomas said, this could be a good argument against the argument that we don't live in a simulation. The world is just too complicated for any computer program, or it's just a super complicated computer program.
The only thing that successfully runs that model is the actual running of the universe.
Is the universe itself. But okay, so what you care about is an interesting concept. So that's a human concept. So that's what you're doing with Wolfram Alpha and Wolfram language. Is you're trying to come up with symbolic representations,
yes,
as simple as possible. So a model that's as simple as possible that fully captures stuff we care about.
Yes. So, I mean, for example, we'll have a thing about, data about movies, let's say. We could be describing every individual pixel in every movie and so on, but that's not the level that people care about. And that's
a good point. Like, even if you're trying to like fully describe an image, right? You start saying like pixel 1 on the right, like pixel 1, and on a grid, I'm not good enough at math to figure it out. Let's say it's 10 by 10, right? And you're like pixel 1 1. That is C. It's got like this much cyan, this much magenta, this much yellow, this much black. Okay, let's go to pixel 1 2. This much cyan, this much black. I mean, at some point you're reducing to an extent where no one is going to understand what the hell you're talking about. That's a really interesting point, like, could you imagine if somebody just, is describing, like, I don't know, I'm going to pick a standard, even though it's not my favorite Michelangelo thing, but okay. The Statue of David or something. And instead of talking about the statue, right? Well, no, it's a pretty good statue. But instead of talking about the statue, you just start zooming in as much as humanly possible. And you start talking about the molecules in marble. Like, it's like you're kind of missing the plot, right? That's interesting. Anyhow, let's continue.
I mean, and that level that people care about is somewhat related to what's described in natural language. Mm-hmm. But what we're trying to do is to find a way to sort of represent precisely so you can compute things. See, one thing when you say you give a piece of natural language, question is you feed it to a computer. You say, does the computer understand this natural language? Well, the computer processes it in some way. It does this. Maybe it can make a continuation of the natural language. Maybe it can go on from the prompt and say what it's going to say. You say, does it really understand it? Hard to know. But in this kind of computational world, there is a very definite definition of does it understand, which is, could it be turned into this symbolic computational thing from which you can compute all kinds of consequences? Mm-hmm. And that's the sense in which one has sort of a target for the understanding.
Yeah, Thomas was saying it would be like describing your drawing now in just ones and zeros. That's all the computer sees, but means nothing to us humans. Yeah. And that's one of the scary parts about the conversation I'm sure that they're going to get into with AI. I'm really curious because it does sound like still his system that he's trying to build is sort of going to get to the point where it can replicate or create things that we have not yet created or solved. And like one of the issues, I know a couple people who work in data science and AI. And one of the things that freaks me the hell out about it, and maybe I'm naive to this, is that I guess a lot of the algorithms, people who work in these spaces don't actually understand the algorithms like fully. Like they kind of do the math. But one of the problems that has arisen in the last few years is like, for instance, if an algorithm has a problem, to go in and fix the code can become really difficult because it's doing machine learning. And so to find the data point where things went off and try to kind of correct it is like a really complicated thing because the human mind can't even comprehend to an extent like the amount of code that's like self-written by the algorithm. So to like make corrections, like quite often they're just going into the code and like tweak this here, what happens? Tweak this here, what happens? Tweak this here, I guess that corrects it. You know what I mean? And it's a little scary when you think about it because it's like we're actually creating systems that we don't fully understand. Now that sounds all doomsday-ish, but at the same time, it's like it's a good point because like you can have a computer, commit calculations that a human mind in a lifetime couldn't calculate. I believe there's a computer that can just run, pi like beyond anything a computer could ever calculate. But like for a human being to go in there and like cross check it is like impossible. It's physically impossible. And that's one of the things that I'm kind of curious if they're going to get into is like who checks to see if it's right. You know, it's an interesting thing. Okay, let's continue.
Natural language, and that's kind of our goal, is to have as much as possible about the world that can be computed in a reasonable way, so to speak, be able to be sort of captured by this kind of computational language. That's kind of the goal. And I think for us humans, the main thing that's important is as we formalize what we're talking about, it gives us a way of kind of building a structure where we can sort of build this tower of consequences of things. So if we're just saying, well, let's talk about it in natural language, it doesn't really give us some hard foundation that lets us, build step by step to work something out. I mean, it's kind of like what happens in math. If we were just sort of vaguely talking about math, but didn't have the kind of full structure of math and all that kind of thing, we wouldn't be able to build this kind of big tower of consequences. And so, in a sense, what we're trying to do with the whole computational language effort is to make a formalism for describing the world that makes it possible to kind of build this tower of consequences.
Well, can you talk about this dance between
Tower of Consequences is a great title for a graphic novel.
natural language and Wolfram language? So there's this gigantic thing we call the internet where people post memes and diary type thoughts and very important sounding articles and all of that makes up the training data set for GPT. And then there's Wolfram language. How can you map from the natural language of the internet to the Wolfram language? Is there an manual? Is there an automated way of doing that as we look into the future?
Well, so Wolfram Alpha, what it does, its kind of front end is turning natural language into computational language.
Right. What you mean by that is there's a prompt, you ask a question, what is the capital of some country?
Right. And it turns into, what's the distance between, Chicago and London or something. Yeah. And that will turn into, geodistance of entity, city, et cetera, et cetera, et cetera. Each one of those things is very well defined. We know, given that it's the entity, city, Chicago, et cetera, et cetera, et cetera, Illinois, United States, we know the geolocation of that, we know its population, we know all kinds of things about it, which we have, curated that data to be able to know that with some degree of certainty, so to speak. And then we can compute things from this, and that's kind of that's the idea.
But then something like GPT, large language models, do they allow you to make that conversion much more powerful?
This is really interesting to kind of hear a little bit of a deep dive into GPT. This is fascinating. For anybody curious about GPT, I believe Jim Lujan used GPT to create poetry about New Direction, our band. And it was scarily pretty well done. All right, let's continue.
Okay, so it's an interesting thing, which we still don't know everything about. Okay, this question of going from natural language to computational language.
Yes.
In Wolfram Alpha, we've now, Wolfram Alpha's been out and about for 13 and a half years now. And, we've achieved, I don't know what it is, 98%, 99% success on queries that get put into it. Now, obviously, there's a sort of feedback loop because the things that work are things people go on putting into it. So but we've got to a very high success rate of the little fragments of natural language that people put in, questions, math calculations, chemistry calculations, whatever it is. We do very well at that, turning those things into computational language. Now, from the very beginning of Wolfram Alpha, I thought about, for example, writing code with natural language. In fact, I was just looking at this recently. I had a post that I wrote in 2010, 2011 called something like "Programming with Natural Language is Actually Going to Work."
Mm-hmm.
Okay. And so, we had done a bunch of experiments using methods that were a little bit, some of them a little bit machine learning like, but certainly not the same kind of idea of vast training data and so on.
Mm-hmm.
That is the story of large language models. Actually, I know that post, a piece of utter trivia, but that post, Steve Jobs forwarded that post around to all kinds of people at Apple. Mm-hmm. And that was because he never really liked programming languages. So he was very happy to see the idea that you could get rid of this kind of layer of kind of engineering-like structure. He would have liked, I think what's happening now, because it really is the case that you can, this idea that you have to kind of learn how the computer works to use a programming language is something that is, I think, a thing that, just like you had to learn the details of the opcodes to know how assembly language worked and so on. It's kind of a thing that's a limited time horizon. But kind of so this idea of how elaborate can you make kind of the prompt, how elaborate can you make the natural language and abstract from it computational language? It's a very interesting question. And, what ChatGPT, GPT-4 and so on can do is pretty good. It's a very interesting process. I mean, I'm still trying to understand this workflow. We've been working out a lot of tooling around this workflow.
From natural language to computational language.
Right.
And the process, especially if it's conversation, like dialogue, it's like multiple queries kind of thing.
Yeah, right. There's so many things that are really interesting that work and so on. So first thing is, can you just walk up to the computer and expect to sort of specify a computation? What one realizes is humans have to have some idea of kind of this way of thinking about things computation.
Let's see here. Thomas Adams said, I've played with it. I asked it to create a table of contents for a game that me and a friend are working on. It did a really good job. Kind of scary. That is a little scary.
Mm-hmm. Without that, you're kind of out of luck because you just have no idea what you're going to walk up to a computer. I remember when I should tell a silly story about myself. The very first computer I saw, mm-hmm. which was when I was 10 years old, and it was a big mainframe computer and so on. And I didn't really understand what computers did. And it's like somebody was showing me this computer, and it's like, can the computer work out the weight of a dinosaur? Mm-hmm. It's like, that isn't a sensible thing to ask. Mm-hmm. That's kind of, you have to give it. That's not what computers do. I mean, in Wolfram Alpha, for example, you could say, what's the typical weight of a stegosaurus? And it will give you some answer. But that's a very different kind of thing from what one thinks of computers as doing. And so the question of, first thing is people have to have an idea of what computation is about. I think it's a very, for education, that is the key thing. It's kind of this notion, not computer science, not so the details of programming, but just this idea of how do you think about the world computationally. Thinking about the world computationally is kind of this formal way of thinking about the world, we've had other ones, like logic was a formal way, is a way of sort of abstracting and formalizing some aspects of the world. Mathematics is another one. Computation is this very broad way of sort of formalizing the way we think about the world. And the thing that's cool about computation is if we can successfully formalize things in terms of computation, computers can help us figure out what the consequences are. It's not like you formalized it with math. Well, that's nice, but now you have to, if you're not using a computer to do the math, you have to go work out a bunch of stuff yourself. So I think, but this idea, let's see, I mean, we're trying to take kind of we're talking about sort of natural language and its relationship to computational language. The typical workflow, I think, is first, human has to have some kind of idea of what they're trying to do. That if it's something that they want to sort of build a tower of capabilities on, something that they want to sort of formalize and make computational. So then human can type something into, some LLM system and sort of say vaguely what they want. And sort of,
this is really fascinating. Okay, I am going to take another break because I just finished another panel, and I've still got a good, 30 to 40 minutes left. Now the question is, do we continue coloring our comic or do we play one game of Risk? I kind of feel like I should just color another panel. But you guys tell me what you feel in the mood for. If you want to watch me play a game of Risk or want me to continue with this interesting conversation. And in the meantime, I'm going to go ahead and play a trailer. And this one, here it is. I believe this is it. Okay.
Hi, my name is Phil Chandler. I'm a freelance artist, illustrator, and cartoonist. Today, though, however, I want to tell you about a graphic novel I picked up recently called Jacob's Apartment. This book was both written and beautifully illustrated by Joshua Kemble. It is the story of a doomed romance that causes the main character to question his beliefs and his faith, while he's also going through other tragedies in his life. Every page has been illustrated by hand and digitally colored with painstaking detail. It is an emotional story that causes you to think and even question things in your own life. And while the story is a tragedy, it is one that I was completely entertained by and I highly recommend. You can currently find this on Amazon or even check in with your local bookstore and see if you can order it. And while you're at it, you can also check out my Instagram at Phil Chandler Arts and also my YouTube channel by the same name, Phil Chandler Arts. And go buy Jacob's Apartment.
My goodness, the ad ended, and I was not here. How dare I? Okay, let's continue. I haven't seen any votes of what they prefer, so I think I will just go ahead and continue this conversation. We're gonna do one more panel and then call it a night, guys. One more panel, potentially. One more panel, I think, is what we can get through. Okay, let's do it.
Of computational terms. Then it does pretty well at synthesizing Wolfram language code. And it'll probably do better in the future because we've got a huge number of examples of natural language input together with the Wolfram language translation of that. Mm-hmm. So it's kind of that's a thing where you can kind of extrapolating from all those examples makes it easier to do that task.
Is the prompter task code also kind of debugging the Wolfram language code? Or is your hope to not do that debugging?
Oh, no. I mean, so there are many steps here. Okay, yeah. So the first thing is you type natural language. It generates Wolfram language code.
Do you have examples, by the way? Do you have an example that is it the dinosaur example? Do you have an example that jumps to mind that we should be thinking about? Some dumb example?
It's like take my heart rate data and figure out whether I
appreciate Lex Friedman pushing a little bit for examples, because again, not all of us are AI programmers, and so I do appreciate the paying attention to the normies out there like me, who, a lot of this like becomes a little accessible, like we found out with analogies. If you create analogies, it's a little easier to digest. Whereas, like, if people are trying to like have me absorb this data, just straight up, it can be a little overwhelming. We got Frank Salazar in the chats here saying, "If you aren't rolling for Taraco, you ain't living." Nice. Is that a vote of confidence for a game of Risk before we call it a night? Is that what you're saying there, Frank, Mr. Salazar, or is that my just wishful thinking? This is just me trying to get out of working on comics for the night. Okay, let's continue.
Make a moving average every 7 days or something, and work out what the and make a plot of the result. Okay, so that's a thing which is about 2/3 of a line of Wolfram language code. I mean, it's list plot of moving average of some data bin or something of the data, and then you'll get the result. And the vague thing that I was just saying in natural language would almost certainly correctly turn into that very simple piece of Wolfram language code.
So you start mumbling about heart rate.
Yeah,
and kind of you arrive at the moving average kind of idea.
Right. You say average over 7 days. Maybe it'll figure out that that's a moving, that can be encapsulated as this moving average idea. I'm not sure. But then the typical workflow that I'm seeing is you generate this piece of Wolfram language code. It's pretty small usually. And if it isn't small, it probably isn't right. But if it's pretty small, and Wolfram language is one of the ideas of Wolfram language is it's a language that humans can read. It's not a language which, programming languages tend to be this one-way story of humans write them and computers execute from them. Wolfram language is intended to be something which is sort of like math notation, something where, humans write it and humans are supposed to read it as well.
That's amazing, actually. I'm interested in the idea of a coding language that we can then actually go in and read without having to take like 50 classes on like Python or something like that. Thomas Adams said analogies are good for people who are in other fields. 100%. And I need to remember that when I'm talking about art. Like when I'm talking about art stuff, turning to analogies is not a bad idea, rather than being like I've definitely talked to like normies with art and been like, oh, the value in this is so great. And they're like, what's value? Because they're thinking value like family values or something like that. And so like decoding what a value is for like a normie who's not constantly thinking about value, saturation, and hue, is probably a good thing. And also honestly, half the time we're decoding normies to make art, where they'll be like, hey, could you just make this pop? And it's like you have to look at it and be like, what do they mean? Do they want like more overlap to create a better foreground, middle ground, and background? Do they want more atmosphere so that we have better atmospheric perspective? Sorry to my people out there who might be flat earthers, I should say more Atmos. I still can't get over the fact that they can't say sphere. I think I've mentioned that on almost every vlog or live stream since. Roll for Taraco said, work first, then risk. I was thinking the value you bring. Nice. Okay, so I agree with Frank. We need to hardcore this. We need to push it, finish this panel, and then we'll rock Risk. If I can't finish this panel in time to play a game of Risk, we will skip Risk, because comics come first. And like Frank Salazar always says, make comics, not excuses. That's a Frank Salazar statement. That is his tagline. And if you want to hear more of Frank Salazar, you should check out Roll for Taraco, or the Taraco Creative Cast, or Salazar Art Nation. Okay, let's continue.
Well, and so kind of the workflow that's emerging is kind of this human mumbles some things, large language model produces a fragment of Wolfram language code, then you look at that, you say, yeah, that looks well. Typically, you just run it first. You see, does it produce the right thing? You look at what it produces. You might say that's obviously crazy. You look at the code. You see, I see why it's crazy. You fix it. If you really care about the result and you really want to make sure it's right, you better look at that code and understand it, because that's the way you have this sort of checkpoint of, did it really do what I expected it to do? Now, you go beyond that.
That answers my question about how do you check
what
the code.
we find is, for example, let's say the code does the wrong thing. Then you can often say to the large language model, can you adjust this to do this? And it's pretty good at doing that.
Interesting. So you're using the output of the code to give you hints about the function of the code. So you're debugging based on the output of the code, not the code itself.
Right. The plugin that we have, for ChatGPT, it does that routinely. It will send the thing in, it will get a result. It will discover, the LLM will discover itself that the result is not plausible. And it will go back and say, oh, I'm sorry, it's very polite. And it goes back and says, I'll rewrite that piece of code. And then it will try it again and get the result. The other thing that's pretty interesting is when you're just running. So one of the new concepts that we invented this whole idea of notebooks back 36 years ago now. And so now there's the question of sort of how do you combine this idea of notebooks where you have, text and code and output. How do you combine that with the notion of chat and so on? And there's some really interesting things there. Like, for example, a very typical thing now is we have these notebooks where as soon as if the thing produces errors, if run this code and it produces messages and so on, the LLM automatically not only looks at those messages, it can also see all kinds of internal information about stack traces and things like this. And it does a remarkably good job of guessing what's wrong and telling you. So in other words, it's looking at things. It's sort of interesting. It's kind of a typical sort of AI-ish thing that it's able to have more sensory data than we humans are able to have, because it's able to look at a bunch of stuff that we humans would kind of glaze over looking at. And it's able to then come up with, oh, this is the explanation of what's happening.
And what is the data? The stack trace, the code you've written previously, the natural language you've written previously?
It's also what's happening is one of the things that's is, for example, when there's these messages, there's documentation about these messages, there's examples of where the messages have occurred otherwise.
Nice.
All these kinds of things. The other thing that's really amusing with this is when it makes a mistake, one of the things that's in our prompt when the code doesn't work is read the documentation. And we have another piece of the plugin that lets it read documentation. And that, again, is very, very useful, because it will figure out, sometimes it'll make up the name of some option for some function that doesn't really.
Nice. Frank said the Artcasters has a huge Flat Earth fan base. They like watching this part of my stream because I'm doing flat colors. It's the second I add the rendering layer, they're just like, I'm out. But like when it's flat coloring, I'm curious about this. How many people who believe in a flat Earth are flat coloring at this moment? I think that would be really interesting, because right now I'm doing what's called flats in color. I'm just kind of curious how that works. He said, let's see, notebooks were created 36 years ago. Nice. Roll for Tarako said, hi, Thomas. Forgive my rudeness for not saying hi earlier. You are not forgiven, Frank. In fact, you are going to be held to the highest standard, and I'm going to set the Inquisition after you, sir. You, sir. Frank, did you catch any of the crazy conversation between me and Jim earlier today? Mr. Lujan is one of the funniest people on the planet. Okay, let's continue.
Read the documentation. It'll have some wrong structure for the function and so on. It's that's a powerful thing. I mean, the thing that I've really
okay, if you ever want to see something really funny, so Frank, you said I am unforgiven. So there's a classic song by Metallica called Unforgiven, but a little known song that they did on one of their worst albums, I don't even know the name of it, but they actually at one point made a song called Unforgiven 2, like a sequel to the song Unforgiven, but it was Unforgiven 2, like TOOO. And it literally was like almost the same song, but then it would say, "Are you unforgiven too?" It's so bad. Anyhow, let's continue.
Realized is we built this language over the course of all these years to be nice and coherent and consistent and so on, so it's easy for humans to understand. Turns out there was a side effect that I didn't anticipate, which is it makes it easier for AIs to understand.
I forgot to mention this too about like regarding Metallica is every time I told a friend of mine this in junior high when they were getting really into Metallica. And this is their later stuff, not their like early thrasher stuff. Like their thrashy stuff didn't do this as much. But it was like when the Black Album came out or whatever, and everybody was like, "Oh my gosh, this is amazing." And I just pointed out to him that like every time the lead singer ends a sentence, he ends it with "wah." There's like a after everything he says. And my friend at the time, who was like a huge Metallica fan, angrily like was like no, and started playing the album to like try to disprove me. And it was almost every single line where it would end with "ooh." And I was like, proven correct, sir. Proven correct. So yeah, that was a side tangent about Metallica ending every line with "ooh ah." There's like a "wah." I feel like, you know, if you were to make an AI script that made Metallica songs, you just need to make sure that the words just end with this. Yeah. Anyhow, they almost sound like a you know, like a preacher, like a street preacher, going like "inda," you know, right? Anyhow, let's continue.
So it's almost like another natural language, but
Yeah.
So Wolfram language is a kind of foreign language.
Yes.
So
Yes.
you have a lineup: English, French, Japanese, Wolfram language, and then I don't know, Spanish, and then the system is not going to notice. Hopefully.
Well, yes. I mean, maybe. You know, that's an interesting question because it really depends on what I see as being an important piece of fundamental science that basically just jumped out at us with ChatGPT. Because I think, you know, the real question is, why does ChatGPT work? How is it possible to encapsulate, you know, to successfully reproduce all these kinds of things in natural language, you know, with a comparatively small, he says, you know, couple of 100 billion, you know, weights of neural net and so on. And I think that, you know, that relates to kind of a fundamental fact about language, which, you know, the main thing is that I think there's a structure to language that we haven't kind of really explored very well. It's kind of this semantic grammar I'm talking about.
All right, guys. We got not too far into this conversation, but it's very fascinating about conversations. Roll for Taraka said I'll have to listen to Metallica again. And the answer to that is again. Okay. That's going to do it for the art part of this stream. I got 3 panels done, which is 1 panel further than I thought I was going to get tonight. We'll probably finish the other 3 later today because I always forget that like 1:30 is today. So we'll set that aside and we're going to go ahead and close out. And I do want to play Risk, but to be honest, I feel like I need to go to bed. Because if I go to sleep, then I'll be able to do this again tomorrow effectively. So I think that we're going to go ahead and call it a little early. I think I was expecting to go for about 2 hours, but we made more progress than I thought I would by the end of the night, and I'm pretty excited about that. I'm not sure what the YouTube link is there, but Frank is sharing a YouTube link. Frank, is that a link to you? I'm kind of curious. Anyhow, I'm going to go ahead and close this out. Oh, he said a new role for Tarako vid. Yeah, you guys should all go check that out. And he said it is my vid. Nice. I will actually probably be watching that before I go to bed. But anyhow, thanks to everybody who's tuned in and watched this. Hopefully it was interesting. We finished about half the page of page 75, and we got some art done, and we engaged the right and the left brain, the left and right hemispheres. So hopefully I didn't kill your the right side of your brain whilst listening to this podcast. Hopefully it was interesting. I just called it a podcast, but it's a vlog, or not even a vlog, a live stream. Man, I'm calling things all sorts of wrong things, which is a good sign that I should go to sleep. Thank you guys, though. I really appreciate you. If you haven't yet, hit the like button. That's gone a really long way to kind of increase subscribers and viewership. And I'm seeing the stats kind of go up on this channel, and I really appreciate it. And that's mostly due to you guys having interest in my art and weird thoughts and stuff, and I really appreciate it. It can't go unsaid how much I appreciate that, and how much that helps me make progress and do things like, consistently working on this comic, which, can sometimes feel like thankless work. And honestly, having you guys hang out and keep me company while I'm working on this lonely thing called cartooning is really greatly appreciated. It doesn't go unnoticed, and thanks, guys. So I will see you on the next live stream, and that will probably be later tonight. So if you haven't, hit that bell so you get notifications when we're about to go live. Hit subscribe and hit like. And have a good night, and make sure you check out that link from Frank too. New role for Tarako. All right. I will see you guys on the next live stream. Goodbye.